Good morning. Uh, to start with today's session, let us take a quick recap what we had discussed in last session. So we have seen that steady state error, and we have discussed a lot about steady state error. What is the nature of the steady state error? Then we had discussed about the response of the system to the unit step response, to be very precise, to the type 0, 1 and 2 type system, and what will be the steady state error that we got in those cases. Also, we had discussed about some static error coefficients that are uh, position, velocity and acceleration static error coefficients and their values and how they contribute in determining the steady state error of a system. Now, moving forward, we'll be going to a second phase of unit number 4, that is transient response. So we have seen that in time domain analysis, if you plot a graph, time versus output, time versus input, then what is the response of the system? So that response is divided into two parts, steady state response and one is transient response. So in transient response, your output of the system is continuously changing with respect to time. Okay, and for that we need to analyze that transient response, and that's why we'll be analyzing the second order system. Okay, we are not analyzing the first order system since it's very simple, but we have to build some concept on this knowledge, so that's why we'll be analyzing the second order system. Now this might have been covered in your electrical and electronics engineering. I'm not sure, but still I'll be uh, discussing it in this session also. So this is a simple RLC circuit, and this circuit makes the system, or this system is a second order system. So we know that what is second order system. So what will be the degree of denominator, or uh, whatever the equation available in denominator, that degree decides the type of your system. So this system is second order system, and what we'll be doing over here, we'll be just finding out the ratio. We'll be finding out the transfer function. So transfer function is Laplace transform of output to Laplace transform of input. So that we are simply interested in determining. Okay, so let us write what is input to the system. This is Vi with respect to time is your input. So it is given by RIT. So this IT is a current flowing through the system. Then we have LDI, differentiation of current dit by dt, and for capacitor we have 1 by c integration of I of t into dt. So this is equation number A, and we'll see what is output, that is v0 of t, it is 1 by c integration of I with respect to t dt. So this is my equation number 2. So these are the derived equation for the complete RLC circuit. Now we take the Laplace of equation A and B. So I'll write taking Laplace transform of equation A and equation B, will get Vi of S, that is the input, it is Ri of S. So I of t, it is I of S now. Then dit by dt. So for that, we have a Laplace transform SLI of S. Okay. And for this 1 upon c integration of I of t to that of dt, it is 1 upon sc into I of s. This is your Laplace transform. Simple Laplace transform formulas we are using over here. Then output is equal to Laplace transform of this. Again, it is same as that of this. So it is 1 upon sc I of s. Fine. So we have Laplace transform of input, we have Laplace transform of output. So we can find out the transfer function as V0 of S, that is output, Laplace transform of output to Laplace transform of input. So it is, if I can write it, it is 1 of SC into I of S divided by, I take out RL, I take out I of s as common term from this. So what I'll remain with R, SL and 1 upon SC. So it is R plus SL plus 1 by SC. And here I have I of S. Okay. Further, I solve this as I cut this I of s and I of s, and if I further make it simplified, so it is 1 upon s r c plus s square LC plus 1, or it is 1 divided by s square LC plus SRC plus 1. Okay. I can further simplify it as V0 of S upon Vi of S as 1 by LC divided by S square plus R upon L into S plus 1 by LC. Now, if we denominator, observe the denominator, the equation, it represents the second order equation. Okay, so it is a second order equation. So that's why I can say that it has two closed loop poles. So this is by observing the denominator, what I can say, it is second order equation, and that's why it is a second order system. It is a type 2 system. Now, this is RLC circuit. Now, we what we will be doing, we will be generalizing this term. Okay, we will be generalizing this term to consider it as a general second order closed loop transfer function. So what we had discussed in your uh, block diagram reduction. So C of S upon R of S. Now it is generalized. I am making it. So it is omega n square divided by S square plus twice zeta omega n S plus omega n square. Sorry, this is not omega n square. This is, yeah. So this is how we are representing it. Now comparing these two equations, what I can write? What is omega n? It is root of 1 by LC. What is zeta over here? Zeta is R by 2 and root of C by L for this RLC circuit. So we have just put those values into this equation to make this equation in a generalized term. Now this your omega n is called as natural frequency. Remember this word. It is called as a natural frequency and your zeta is called as damping factor. Zeta is called as damping factor. Okay, I'll explain these two terms in detail. But before that, to check whether you are awake or you have not, whether you are attentive, can anyone tell me what is damping factor? Can anyone tell me what is damping factor? Or rather, what is damping in terms of mechanical systems? So we have discussed the spring mass damper system. You might have undergone this spring mass damper system quite a lot of time. Can anyone tell me what is damping? Anyone? Anush, can you tell me what is damping? Okay, fine. Let us move forward. Let us go for these two terms. First is your
Correct.
damping. Yes. Uh, who's talking? Please go ahead.
The radio stop.
Yeah, yeah, Anush, go ahead. It's okay if it is.
Effect of effect.
Okay, fine. Anush, you are not audible, I suppose. So it's okay. I'll explain it. So, what is damping factor, or in other terms, what is damping ratio? Now, we know that whatever the response of the system, that can be broken down into its transient response as well as its steady state response. This we had discussed. Now, a certain time is required for a system to reach the steady state value. Okay. Now, during this time, the system either oscillates or it increases exponentially. Let me explain it with the help of the graph. So, this is T and this is your output response, and this is the desired value that you want. So, there are in transient systems, the system either oscillates and come to steady state, or what happens, it output rises exponentially until it reaches to the steady state. So these are the two conditions are there. Now every system requires certain time, certain amount of time, like over here this is a steady state. So this much of time is required for a system to either die down the oscillations or reach up to the steady state. Now, every system has a tendency to oppose any oscillatory behavior. Like a simple example, you might have while riding your bike. Okay, your bike, if it goes to the path hole, and the shock absorbers they oscillate for a certain duration of time. Okay, and after that, because of whatever the oil present in the shock absorber, and whatever the damping factor of that shock absorber, what happens, that system has tendency to oppose those oscillatory behavior. If that was not the case, what happens, your system continue to oscillate for the infinite amount of time. So it is not a desired condition. So that's why we have the systems that those are having the tendency to oppose any oscillatory behavior. Okay. Now this opposition to oscillation is called as damping. So opposition to oscillations oscillations is called as damping. Remember this important term. It is not with reference to mechatronics, but generalized being a mechanical engineer, you must know what is damping. Now, this damping is measured by a factor called as damping ratio. Okay, higher is the damping ratio, there will be more opposition of the system to the oscillation. Okay, we'll discuss this damping ratio and effect of damping ratio on the system response in detail. But for that, you must able to understand what is damping and what is damping ratio. The next one is your natural frequency, or it is called as natural frequency of oscillation. Natural frequency of oscillations. This is denoted by omega n. Now, when there is no damping, that means your zeta value is 0, there is no opposition to the oscillation. So, in that case, there is no opposition to the oscillation. Okay, and the system oscillates naturally. What happens in that case? Your system oscillates naturally. Okay, and when zeta is equal to 0, the system oscillates with maximum frequency. What happens? Zeta is equal to 0, your system oscillates with maximum frequency. Maximum frequency, that is naturally, and that maximum frequency is called as natural frequency of oscillation of a system, and it is denoted by omega n. Okay, so that is what we call as natural frequency and damping factor. Got my point? So this is a system, this is a second order system, and we are trying to establish the relationship or establish a concept of transient response with respect to this second order system. Now, there are few things like poles and zeros that we have discussed in unit number 2, I suppose. So in that, we have defined that the position of the poles defines your what I can say, the stability of the system. Okay, with the help of S-plane graph. Fine. Now, your second order system, it exhibits a wide range of responses which need to be analyzed, and they can be described as compared to a first order system. First order system is very simple system, but second order system is having a very wide range of responses. There are many possible type of responses that needs to be analyzed. Now, if we change your system parameter, there is a change in the form of a response. And as we know that the second order system has two closed loop poles, these two closed loop poles can move anywhere in the S plane when the system parameters are changed. Now let us see what are the change in this location of poles, and what is the output response of to the system for a unit step response. Okay, again we are dealing with unit step response. Before that, let me once again tell you the S-plane graph. So on S-plane graph, we have one imaginary axis, okay, and one real axis. Over here we put the imaginary numbers, and over here we put the real numbers. Got my point? So here we'll be making a comparison, or we'll making an analysis if the closed loop poles. Now what is closed loop poles? If we go for this system, so if we find out these roots of the equation, and if we compare this equation with 0 and find out the roots of the equation, then we get the poles of the for that second order control system. Okay. Now, depending upon the position of the poles, what will be the system response? So here we have closed loop pole position, and also we have response output response to a unit step input unit step. Okay. Now the first case is uh, you are having the poles like this, the pole position like this. This is an imaginary axis. I sorry j omega. This is zeta. So when the poles are on the left hand side of the S plane, and they are real poles, the system output response is something like this. So this is T, and this one is your CT, and this is the desired value. So it goes like this, and there is a certain steady error. Second case, when your poles are located over here and the same number on the real axis left hand side, and they are having the same poles, then we can say that the system response is good, like this. It rises exponentially and there is no steady state error. Now we have the third condition, when there are distinct poles which lies on the left hand side of your imaginary poles, we can say that left hand side of S plane. So in that case your system oscillates, and it takes some time to die down those oscillations like this, and there is a certain steady state error remains. Also, we have, if there are a pair of complex conjugate number, then your system is totally an unstable system. So how it look like if we are having this desired magnitude? So the system is something like this. It behaves like this. So what is the desirable condition? It is a favorable condition. In some cases, this is a favorable condition. So this is how, by the location of two closed loop pole position on the second order system, for the second order system, these are the output responses for the unit pole. Now let us discuss what is the effect of uh, zeta on your position of these closed loop poles. Closed loop poles. So first case, let me for you people, let me find out the pole first, so that you will get how to find out the poles. So this is our closed loop transfer function, s square plus twice zeta omega n s plus omega n square. Now you know that zeta is your damping ratio and omega n is the natural frequency of oscillation. Now the closed loop poles are, we have to compare this denominator equal to 0. So s square plus twice zeta omega n s plus omega n square, we compare it with respect to 0, so that your transfer function is infinity, and in that case you will find the poles of the system. Now that's why I can say that this s is equal to uh, minus zeta omega n. If I solve it, taking the roots of the equation, it will be omega n in bracket under root of zeta square minus 1. So these are the poles S1 and S2. So these are the closed loop poles for the system. This is plus minus. So first closed loop pole is minus omega n plus omega n under root of zeta square minus 1, and second one is S2 is minus zeta wn minus wn omega n root of zeta square minus 1. Now, for a given system, if this omega n natural frequency of oscillation is constant, and that's why the position of the pole is depend on the value of zeta only, that is the damping ratio only. Now, what are the conditions? There are four cases where your damping ratio, change in damping ratio will change the position of the closed loop poles. Now, when your zeta is lying between 1 to infinity, so in that case, I can say that S1 and S2 are equal to minus omega and zeta plus minus omega n zeta square minus 1. So therefore, I can say that S1 is minus omega n zeta, zeta omega n plus omega n root of zeta square minus 1. This is first pole, and S2 is equal to minus zeta omega n minus omega n to root of zeta square minus 1. So these are the two poles. Now if we see these two poles, that these two poles are real, unequal and negative, which is shown in your figure number 1. Okay, so let us go back. So these are the poles. Okay, so these are your real poles, unequal poles and negative poles, because they are lying on the left hand side of your S plane. So that's why the system response is shown like this. Now second case, if damping ratio is 1, we get S1 S2 is equal to minus zeta omega n plus minus omega n 1 minus 1, or we can say that S1 and S2 is equal to minus zeta omega n equal to minus omega n, since your zeta is equal to 1. Okay, so what is S1 then? S1 is equal to minus omega n, and S2 is equal to also minus omega n. Now here both the poles are at minus omega n, that is there is a double pole, that is there is a double pole as shown over here. So it is overlapping. So for the sake of convenience visualization I have shown, but these are the double poles with a negative value. So in that case the system response is like this. Now the third case is this, when your omega is ranging from 0 to 1. Okay, now as your zeta is less than 1, your minus zeta square becomes complex, and it can be written as j of 1 minus zeta square. So that's why your S1 and S2 becomes minus zeta omega n plus minus j omega n. Here you have a imaginary part included into this, and 1 minus zeta square. Okay, so what are these kind of poles? These are this forms a complex conjugate pair. Complex conjugate pair of the roots of the equation. Now that is shown over here. So this is a complex conjugate pair of the roots of the equation. So these are the position of the closed loop poles. So in that case, your system finds an oscillations. Okay, and the fourth term is when your damping ratio is 0, then in that case we get S1 S2 is equal to minus omega zeta omega n plus minus j omega n 1 minus zeta square. So since your zeta is equal to 1, that's why it is 0 plus minus j omega n 1 minus 0. So it is can be shown that S1 and S2 is equal to plus minus j omega n. So what is this case? In this case, S1 is equal to plus j omega n and S2 is equal to minus j omega n. So these poles are no real part. So these poles are no real part. Only the part which is available is imaginary one, and that's why it lies on the imaginary axis. And when the poles lies, both the poles lies on an imaginary axis, the system will oscillates like this. Fine. So this is the system response based on the closed loop poles and the effect of value of damping ratio on the on the response of the system. Fine. So this is one thing, and the second thing I would like to tell you is the what I can say the various transient time responses specifications that I would like to convey to you, which is a very important point. Now, in steady state response, the steady state response is defined or it is explained with only one parameter, that is your what we can say the steady state error only. Okay, but this transient response that is having some other specification. The transient response specifications. Transient response specifications. These are important one. Now, as I said earlier, all the transient response that we have studied, underdamped response is important. Now, what is underdamped response? So, underdamped response is it's a what we can say that there are overshoots and undershoots, but they are having certain up to certain level, that is called as underdamped response. And in case of underdamped response, your output goes above the input value, and that can be little bit dangerous, so that we don't want. But if it goes to certain response, certain specified level, it is fine. Now we define the transient response for uh, the unit step input. Now the typical transient response for the unit step input is represented by this diagram. So this diagram is very important as far as transient response is considered. This is C of t. Now we have this unit step standard input signal. We have this uh, overshoot value as 1.02, and we have the undershoot value that is equal to 0.98, and here we have something over here we have zero point 0.5 value, and over here we have a 0 value. Okay, so our graph for the underdamped system is goes like this. The system oscillates, and the oscillations die down after certain level, and we'll get the steady state response. Fine. Now let me explain the various specifications. Important time specification. First is your delay time. first specification is your delay time, that is represented by TD. Okay, so what is TD over here? It is called as TD. This one is TD. What is TD? Delay time is the time required for a response to reach 50% of final value in the first attempt. Okay, let me repeat the sentence. It is the time required for the response or for the output to reach 50% of the final value of the final value in the first attempt the first attempt. So over here, what we are expecting the response, we expected the response to reach at this value 1 for a unit step response, unit step input. But the time taken, there is certain finite amount of time taken by this response to reach 50% of the final value while starting from in the first attempt. That time is called as delay time, and that delay time is given by 1 plus zero point 0.7 zeta upon omega n seconds. Remember this equation. Remember this equation. So zeta is your damping ratio, omega is natural frequency of oscillation. This is what we call as delay time. Second specification is known as rise time, and it is written as T suffix R. Okay. Now what is rise time? I'll mark the rise time over here. So this much of time is called as rise time. Now, what is rise time? It is the time required by a response to rise from 10% to 90% of the final value. It is the time required for the response to rise from 10% to 90% of the final value for a overdamped system. If we consider the underdamped system, it is the time taken for the response to rise from 0 to 100%. Okay, so for overdamped system, if the system is overdamped, then for that, if the response, the time taken to reach the response from 10% to 90% of the final value of the final value. Here, final value is 1. And for underdamped system, under damped system, it is the time taken for the response to rise from 0% to 100% of the final value in the first attempt. Okay, it is given by the formula TR is equal to pi minus theta upon omega d seconds. Okay, third specification is your peak time. Third specification is peak time. It is represented by T suffix P. So this is what we call it as a peak time. TP. So this time is called as peak time. Now, what is peak time? Peak time is the time required by a response to reach its first peak. This is the first peak, this is second peak, this is third peak, and this is fourth peak. So it is the time required by a response to reach its first peak. First peak is called as the peak time. Okay, let me make clear that this is a graph representing time versus nature of the response, and as the response progresses, it takes some finite amount of time to show the system a different kind of responses. Okay, so that is those time we are discussing right now in the form of transient response specification. Now this coming back to peak time is given by the equation Tp is equal to pi upon omega d seconds. This is what we call it as a peak time. The fourth specification is your peak overshoot. Peak overshoot. This peak overshoot is represented by m suffix p. So this is what we call it as a peak overshoot. What is peak overshoot? It is the maximum peak value of the response measured from the input signal value. It is what is peak overshoot? It is the maximum peak value that we are getting in a particular input signal that we have provided. It is also we can call it as it is a maximum error between input and output. Okay, what we need our this is our input. This is our input unit step input. We want output to be proportional to input, but it is going beyond the input. That's why the system needs to be over here on this line, one line having unit step response, but it is going beyond that line, and that is why it is called as an error. So overshoot can be also called it as a maximum error between input and output. It is also called as maximum error between input and output. Now this peak overshoot can be written in form of percentage. So percentage of peak overshoot is equal to E raised to minus zeta pi divided by 1 minus zeta square. This is e to the power into 100. So this is what we call it as a peak overshoot. And the last uh, response or the specification is your settling time. This is your settling time. Now let me represent the settling time over here. So this entire time is called as your settling time. Now what is settling time? Settling time is the time required for a transient damped oscillations. So here there are oscillations and they are damped with as the time progresses. Okay, and those oscillations are died out and they stay within the specified tolerance band. So these oscillations will be stayed excuse me within the specified tolerance band. Over here it is the 2% of input value. Okay, so the oscillations are remain within that particular band, and whatever the time required by a response, time taken by a response to reach into that particular phase where the response remain or stay within the specified tolerance band, that is called as your settling time. And settling time is given by the formula Ts is equal to 4 upon zeta omega n seconds. So there are different types of times that are required for developing the transient response specification. Let us revise those. First is delay time. It is the time required for sys response to reach the 50% of its final value in the first attempt. Rise time for the overdamped system, it is the time taken by response to reach 10% to 90% of the final value. And for the underdamped system, it is the time taken by a response to reach from 0% to 100% of the final value. Then we have a peak time. It is a time required taken by a response to reach its first peak. Okay, and it is also called as the maximum peak value, the maximum value that the response is attaining. And we have peak overshoot. It is what we call it as a maximum peak value of a response measured from the input signal value. It is also called as maximum error between input and output. And the last one is your settling time. Now, this settling time is the time required for the oscillation, for a transient damp oscillation to reach and stay within the specified tolerance band. That is what we call it as a settling time. Fine. Now, let us solve the problems on this transient response. A simple problems are there. So let us solve it. We have to find out the time domain specifications. So whatever we have discussed these times, those are called as time domain specifications. Find out the time domain specifications for a system having transfer function equal to 1 upon s square plus s plus 1. Can anyone tell me which type of system, what is the order of the system is this? Depending upon the degree of denominator, degree order of the equation in the denominator, we can say that this is a second order system. Now our equation is of the form is omega n square upon s square plus twice zeta omega n plus omega n square. Now we compare this denominator with this equation. Okay, we can get that omega n square is 0 1. That's why omega n is equal to 1 rad per second. Okay, compare these two equations simply. S square plus twice zeta omega n plus omega n square, which is equal to s square plus s plus 1. Now what is omega over here, omega n over here? Omega n square, it is 1. So that's why omega n is equal to 1 radian per second. Now twice zeta omega n, what is this? Twice zeta omega n over here with this equation, this is again 1. So that's why, therefore, damping ratio is 0.5. Fine. Now we find out first what is damped frequency omega d, because it required in our finding out the time domain specification. So omega d is omega n to root of 1 minus zeta square. Okay, so it is coming out to be 0.866 radian per second omega d value. Now we'll find out theta. Theta is also required. So what is theta? Formula for theta, it is tan inverse of 1 minus zeta square divided by zeta radians. Okay, so that is why theta is equal to 1.40471 radian. So you have to remember these two formulas, found out the omega d and your theta. Now let us find out first what is natural frequency. These are the time domain specifications. So natural frequency of oscillation is omega n is equal to 1 radian per second. Second thing, damping factor. Second thing is damping factor. That is your zeta value. So what is zeta? Zeta is equal to zero point 0.5. Remember, we are talking about time domain specification. With the help of transfer function, we are finding out the time domain specification for a given system. The third one, delay time, TD. What is delay time? Delay time is equal to 1 plus zero point 0.7 zeta divided by omega n. We know what is zeta, we know what is omega n. Based on that, we can find out it is 1.3 second, 35 second. Now, what is this delay time? It is the time required to reach the response from up to 50% of its final value in the first attempt. So this much time taken by a system to reach up to 50% of the final value. The fourth one, rise time, TR, it is pi minus theta divided by omega d. We know all these values, so it is 2.418 second. What is rise time? What is rise time? So rise time is the time taken by a system, what we can say, for the over system it is 10 to 90%, and for under system it is 0 to 100%. Okay, so that is what we call the rise time. Then the fifth one is your peak time, reach up to the maximum peak. So Tp is equal to pi divided by omega d. So that is pi divided by 0.866. So it is coming out to be 3.627. So when the system, what is the peak time? That is the time taken by a response to reach up to the maximum peak. That is what we call as the peak time. So check this time. Delay time, then delay time, if we add on it, it is up to 50% delay time, it is up to 100% rise time, and maximum peak after reaching to 100%, it will go beyond the particular set point value. Then again, this time is increased one. Then we have percentage overshoot. Percentage overshoot, it is equal to 100 into e to the power, we have minus pi zeta 1 minus zeta square. So it is 16.30%. Maximum or peak overshoot is 16.13%. And the last one is your settling time. It is a time required for a response to settle down or to reach and settle down between the specified tolerance band. So it is given by zeta into omega n. So it is equal to 8 seconds. So this is a maximum time. You can check it over here. Settling time is the maximum time. The lowest time is your delay time. If you built on it that you are having rise time, then you have the peak time, then you have the maximum peak overshoot, and then you have the settling time. So if you remember this diagram carefully, you can easily get what are the various transient response specification that are available for the second order system. Okay, so I think that's all for today's session. I'll stop here and we'll discuss the remaining things in the next session. Now you can put your attendance in the chat box and you can now log off the session. Thank you.